Welcome, chemistry students. So we continue our discussion on acids and bases. Specifically, this time though, we're going to look at the equilibrium of weak acids and bases. Before we start, I want to make sure to tell you that this is going to be part one of two. In this video, we're going to go over examples, up to example 4. And in part 2, we're going to go through examples 5 to 7, just so that we don't make this video too long and it's more easily digestible that way. Okay. So a bit of review to begin. Here we're looking at the weak acid and base definitions. So essentially, both of them, weak acids or bases, they don't completely ionize in water, and I'll define that more specifically in just a bit. Of course, weak acids don't produce the expected amount if they were to completely dissociate, amount or concentration of hydrogen ions, whereas bases don't produce the expected concentrations of hydroxide ions. Those are weak bases. Okay. Now, you're going to see this general form of the reaction or the ionization of an acid and base, and I want to make sure that we go over it and not ignore it. So this is your acid HA, just generally represents an acid, any kind of acid, with your hydrogen or proton here. So this acid, look at its conjugate. Doing a bit more review here. Its conjugate would be a conjugate base, right? Water would have accepted, you can see how it's accepted that proton. So water would have accepted a proton, which would make it by definition, according to the Bronson-Lowry definitions, which would make it a base. And hydronium here would be your conjugate acid. Okay, so that's just a general ionization reaction for an acid in water. Notice that A just represents any kind, any anion that would have, of course, appeared here in this weak acid HA. Okay, now for the base. B is your weak base. And this base is, of course, going to behave like a base. So it's going to, you can see here, accept. It's going to accept a proton, which defines it, therefore, as a base, hence the B, which makes this a conjugate acid because it's going to likely give up this hydrogen if it were going in the reverse direction. And water here, we can look at the conjugate pairs here. Water, we see that it's lost a hydrogen ion, so it's going a hydrogen ion or proton. In the reactant side, it behaves like an acid, and in the product side, it behaves like a conjugate base. Okay, so this is just again the general form of the ionization of a base in water. Okay, little smudge here. Remove that. Okay, just a bit of review, and also just to keep it simple, um, we can ignore this fact. We know that Kw is quite low. We know that water will self-ionize. Distilled water will self-ionize. From this ionization constant of water, we know the concentration of hydrogen ions is extremely low. Right? And for this reason, we're going to keep it simple. We're not going to take that into consideration when doing future examples. It'll make more sense when it's in context, but for now, we don't have to worry about the concentration of the self-ionized amounts of hydrogen ions or hydroxide ions. Okay, you can, and you'll see that it's not going to significantly affect your results moving forward. Okay, you're also going to see a lot of these, a lot of questions refer to something called percent ionization. So percent ionization is essentially just similar to what how you would figure out a mark on a test, let's say, or a mark on a quiz. And it's really just the concentration of an acid or base that actually ionized versus how much versus what it what we would expect it to be if it had fully ionized. So if it were a test or a quiz, what did you get over what you could have earned, right? Times 100%, and that's that. And here's that more precise definition of what a weak acid and base is, just the generally accepted amounts. So if an acid or a base it will be classified as a weak acid or base, then that just means it would have to be less than 50% ionized. Okay, so the percent ionization defines whether an acid is weak or not, or a base is weak or not. Okay, so now all of this hopefully will be put into context as we do our first example. Okay, so here it's asking us to calculate the ionization constant. Let's say it again. Calculate the percent ionization from a given pH. Now, this lesson could actually be very short because that's essentially all the concept um, behind the equilibrium of weak acids and bases. Maybe a few more tidbits here and there, but I'm going to try to do a lot of examples to hopefully get you ready to practice yourself and to feel better about what you're doing. Okay, so first it's given as a pH, or rather the pH of this concentration of a solution of methanoic acid is 2.38. Back to organic chemistry here. Methanoic acid is 2.38. So that's our pH value, and this is the concentration. Now, what is the percent ionization? So that's this is the first kind of question we've done of this sort. So we start at the beginning. Let's analyze this. Okay, percent ionization. Okay, we know that is the concentration of acid or base. In this case, it's acid that actually ionized. Okay, and that is over the concentration. We're going to say that we would expect if it were to completely have ionized. Okay, so let's say concentration of acid fully ionized. Okay, or sometimes you might see this as the initial concentration of the acid, but I paused for a moment as I was writing this because I don't think, oh, I forgot, we should write 100%, because I don't think that is a perfect definition. It could often work, but if we just write initial concentration, it may not actually work, and this is why. In this case, methanoic acid is a monoprotic acid, so what that means, again, is that it just has one proton. Okay, so this will ionize. Okay. And at this concentration, 0.1, right, given to you in the question, it should completely ionize, right? So I think the better definition, what you might see in some textbooks or online, is that, again, the denominator would say this concentration of your acid at your initial value, or the I goes before it. But this is wrong, because that would mean that this is what you're going to write there. And although it is what you're going to write there, because it only works out because this is a monoprotic acid. If it weren't, you would have to multiply it by 2 or by 3. So it's just going to be 0.1 in this case, right? That's how much we would expect the concentration to be if it completely 100% ionized. Okay, sorry for that winded explanation. Hopefully that makes sense. I'm going to add a page here because I'm missing, I need some room. Okay, so remember, we were given pH. Okay, we were given pH. Now, we can figure out what the concentration of the hydrogen ion is in this solution through this formula, right? Back to grade 11 and review we did in a lesson or two ago. Okay, so that means 10 to the negative 2.38 is going to give me the concentration of hydrogen ions in this solution. So that is just, and I have this pre-calculated here, 0.004 moles per liter. Okay, back to our ionization percentage. Okay, and we have how much acid actually ionized. Okay, and 0.1 is what we would have expected to be completely ionized, right, in a 1-to-1 monoprotic ratio. And what we get, again, I forget to write this down often. Okay, is 4.17%. Okay, that's it. So that's your answer. The self-ionization of methanoic acid given this concentration and this pH is 4.17%. Okay, next example. So here, the pH of a 0.5 mole per liter solution of ammonia, right? So this is similar to the previous question. We are calculating the percent ionization again, except it's not of an acid, it is of a base. So we're dealing with ammonia here, a Bronson-Lowry base. So I'm going to switch over now to I forgot to do it for the first practice example, but I'm going to switch over to this because I like how it flows better. Okay, so this is ammonia. Ammonia, there we go. Ammonia in water HOH, and you'll see me write HOH more often than H2O because I like how that works better. You'll see why. What happens with this, we know, is that we're going to lose that hydrogen ion. See, that's why I like to write it like this, HOH instead of H2O. We're going to lose this hydrogen ion. We're going to produce ammonium, right? And from the question, I'll toggle back to that. From the question, we have 0.15 moles per liter of ammonia. Okay, so 0.15, 0.15, right? Okay, no concentration really for water. I'm just trying to make sense of all this, right? This is a 1:1:1 ratio. Remember, I should write this down. This is a liquid, this is aqueous, this is aqueous, and this is aqueous. Okay, so no concentration for water because that doesn't make sense. But it's all a 1:1 ratio, so we should get this, right? We should get that. Okay, then the question also says to us, just toggle there, that it has a pH of, right, a pH of 12. So pH of 12. All right, now that means let's figure out pOH. We can do that because we have pH, because we also know that 14 is equal to pH plus pOH. So a bit of grade 9 math here, and we can figure out what pOH is. And the reason we're thinking of doing this is because if we figure out from the pH what the actual pOH and what the actual concentration of hydroxide ions is, what the actual amount is, then we can compare that to this in our percent ionization formula. Okay, so that's the analysis part. Let's do that then. So pOH is just 14 minus pH. And because we know what pH is given to us in the question, it's just 14 minus 12, we know then that the pOH of this solution is, this aqueous solution, is 2. So with that, we can then calculate the actual hydroxide concentration, right? That is 10 to the negative pOH. That's 10 to the negative 2, right? 2 right here. Okay, plug that into your calculator and we get this 0.01 moles per liter. Again. All right, so now we know what the actual amount is. Compare that to what we expected if it completely dissociated, and put that into your ionization, percent ionization formula. So what we actually have right? And what we would have expected if it completely ionized. And we get 6.7% as our answer. Okay, so hopefully that made sense. Again, post any questions. Okay, now this was actually originally a lesson within a lesson talking about the 5% or the hundreds rule, but you've already seen a whole presentation on that, a whole lesson on that, so I'm not going to delve into this anymore because there's a whole video posted on just this topic, so skipping over that. Okay, now, so we've looked at percent ionization, pH, defined, I think, more clearly what a weak acid and base is. Now let's get into our Ka and Kb constants. These are ionization constants for acids and bases. Ka and Kb. A for acid, B for base. Okay, I'm going to try to stick with writing this in this program. Okay, remember the general ionization formula for a base and an acid? Well, they're here again. So we're going to do what you've seen done in the past and just write a Kb for the base, Kb expression. We know that's products over reactants to their exponents. In this case, it's all 1:1, so it should be pretty simple. I'm hoping you're visualizing this as I'm writing it. So let's do it. This is a B. It looks like an O, but it's a B. Okay, and then just over in our denominator is a B, right? We don't include water because it's liquid. Okay, Ka is again products over reactants except for water, so that's just HA. Okay, so these are the ionization constant expressions for a base and for an acid. And these Ka, Kb values will tell you the equilibrium of the solution, so how forward or back it is, forward or reverse it goes. Okay, and it's necessary here. So we're going to write the ionization constant expression for acetic acid. Okay, we're going to see that we're going to work with acetic acid quite a bit. It's a great weak acid to consider when we're looking at these examples, but we have to first write the formula down. So acetic acid, and if you don't remember what it is, after a few examples, it'll be etched in your head. Okay, so that's acetic acid. Back to organic chem again. Okay, H2O or HOH. I always forget states. Don't think I gave myself enough room here. Okay, we know that the acetic acid being an acid will donate a proton. Water will accept it to create hydronium. Okay, and that then creates right, acetic acid, water, hydronium, and your acetate ion. Okay, this acetate ion is going to give us a bit of work in the future, but we will get to that. All right, so that is our formula. Now our Ka expression from here, again, is just products over reactants. So H3O plus, our acetate ion. Okay, ignore water. Okay, that's it. That's our Ka expression. Right then, moving on. Okay, example. So now we're going to calculate. Ka from percent ionization. Okay, we've done a few examples, a couple of examples where we calculated percent ionization from pHs for an acid and base. Now we're calculating Ka from percent ionization. So calculate, and this is the last example we'll do, and we'll stop. I'll stop this this video, part one of it, and we'll continue in another video. So calculate the acid ionization constant Ka of acetic acid, right? We saw that formula. If this is the concentration, right, 0.1 molar concentration solution at equilibrium has a percent ionization of 1.3%. Now, there is more than one way to do this. I am going to attempt to show you what I think is the faster and easier way. There is another way. If you find this way of doing it, that's great. There is another way, and I'm going to more easily write here. So I'm going to switch to that. Just erase all this ink. Okay. So ice table. Just correct my pen here. Okay. Ice table HC2H3O2 in the presence of water. Okay, so ice table. When in doubt, draw an ice table. Okay, 0.1, right? That's concentration given to you. Look, I'm not lying to you. Concentration given to you. Well, that was badly drawn, but I was attempting to circle it. Okay, so the concentration is given to you, 0.1. Okay, we know that we can ignore water because it's a liquid. Now, at time zero, if you recall, nothing here. Okay, now what's kind of tricky here, what you have to think about is the question gives you a clue. It says that 1.3% of the solution ionizes. So 1.3% of this will actually ionize. So this concentration will decrease by 1.3%. So let's do that. So if we know the concentration, the percent ionization, right, is 1.3%, right? So 1.3, well, that was bad. It's not a 3. So 1.3% is equal to, right, what we expect it to ionize to, right? So it's actually this value. Okay. I'm tempted to call it X, but I'm not going to call it X. I'm going to say concentration of, okay, conjugate base. Right, this is the conjugate base, right? Acid conjugate base over, we know that it is, this value here is 0.1 over acid, right? Solving for this then is essentially just multiplying this. Remember, it's a percentage, so okay. So we know then that this is the concentration, right? We know that this is actually going to be minus x. This is going to be plus x plus x. It's all 1 to 1, so the amount that this has changed is all going to be proportional in a 1 to 1 to 1 ratio. So we can write then the same thing all across the board, making sure to take our signs into consideration. Okay, so fill in E, add I and C, and we get 0.0987, and these we just rewrite. Good. So Ka, our Ka expression for acetic acid. I'm just plugging things in from the ice table here. Okay. All right, so finally get to our answer. We know our concentrations at equilibrium. Our percent ionization gave us that clue how much actually ionizes, what the value of these concentrations are. We worked backwards from there in a 1 to 1 to 1 ratio, as a 1 to 1 to 1 ratio. Remembering that these signs at these concentrations of reactants decrease where products increase. We then know the values at equilibrium, plug that into your Ka expression, right? We reviewed what where this comes from, how this looks, plug in our values, and we get 1.71 times 10 to the negative 5 as our Ka value. Okay, so hoping that that makes sense. Again, post any questions if it doesn't. So back to our lesson. I know I'm going to stop there after our first 4 examples. So we'll continue with this in our next video. Hope this helps.